Hello, my children. This is a Unit 1 review video, which is from Semester 1. This will be on your Semester 2 final, so make sure to pay attention, take some notes. Okay, there's three things I'm going to review mostly. There's more to the unit, but these are the most important parts. So first thing is these three terms, okay? Volume is essentially the space that's three-dimensional that things take up. So space 3D that take up. So for example, if you have two boxes, one's this big and one's this big, this would have the bigger volume. Okay, temperature is related to technically the average kinetic energy, which is energy of motion. But in terms of models and talking about it, a lot of times we just talk about how fast particles are moving. So higher temperature, particles move faster. And then pressure, for a gas, pressure is caused by the collisions of particles with a surface. I know my handwriting's bad, but listen to me and then you can still know what I'm writing. Collisions of a particle with a surface. Okay, and this is from random molecular motion. Okay, now pressure, I put it on here twice, even though I just said it. Because what you need to be able to do is take things like this. Let's say there's 4 particles in here. And then here's another one, same 4 particles, but now the volume is less. And you need to be able to explain why the pressure is higher. Well, we know these are moving around randomly, and so if there's less space, that means you have more collisions with the surface, and therefore a higher pressure. So you got to be able to explain stuff like that. It's not too bad, not too bad. Let's do a couple more. So let's say you take a sample of gas. Here, I'll do it in a cylinder. I feel fancy, guys. Okay, and it's got 3 particles in there, why not? And then you add some fire. Wow, that's fire. Okay, maybe with a slight touch of yellow here. Okay. And so we heat this up, so the temperature increases, which means faster particles, right? Here, we'll put little arrows on them so you have an idea of how fast they're moving. And then we've got the same container. It's a rigid container. This is like a metal container, so it can't expand. But since the faster particles are moving, you're going to have more collisions. And of course, you could do the opposite of all these things, and therefore more pressure. Okay, very good. Last thing I'm going to talk about is the combined gas law, and we'll look at an example problem. Okay, so combined gas law is P1 V1 over T1 equals P2 V2 over T2. And this is the combination of Boyle's, Charles, and Gay-Lussac's law. There might only be one S there, I'm not sure. And so you can cancel constant variables, and then you plug in and solve for your unknown. What else? Also, always convert to Kelvin. I don't know. Let's see if I find anything else. Here, I'll annotate in a different color. So I've got 2-liter balloon. It's heated. That's a typo. From 20 degrees C, it expands to 2.5 liters. What's the final volume? So I'm looking for V2, final volume. It's given me V1. It goes from T1. Oh, that doesn't make sense. This is the final volume. Okay, we'll solve for temperature then. I really should have proofread this before I made a video, but I'm not going to fix it, so it's okay. So I'm looking for T2 then. Okay, so I'm going to assume pressure's constant, so I cancel that out. I have V1 over T1. If pressure is not constant, there's no way for me to do this. So the only choice I have is to assume it's constant. And it doesn't tell me anything about it. It's a balloon, so most likely the pressure's not also changing. But I guess it could. I don't know. Alright, so we plug this in. We get 2 liters over T1. But remember, you have to add 273 to make that Kelvin. So this is 298 Kelvin. 298 Kelvin is equal to V2 is 2.5 liters over T2. You could solve for T2 first, by the way, if you wanted to. I'll switch to purple. So we can cross multiply here because the variable we want is on the bottom. So here, I'll put that. Cross multiply when unknown on denominator. That's true for just about all algebra ever. 2 liters times T2 is equal to 2.5 liters times 298K. I want the T2 by itself, so I do the inverse of 2 liters, which is division. This divides out. I can get my handy-dandy calculator. Okay, 2.5 times 298 divided by 2. So 372.5. So it makes sense that it is higher because it says it's being heated. Now if we wanted to, we could convert this to Celsius by taking away 273, which would give us mental math. Oh no, not 2. So it's a little bit bigger. So 99.5 degrees Celsius. I think I did that right. Yeah, because if that were 373, it'd be 100, but it's 1.5 less. Okay, so there you go. That's a little review on gases. I have a little bit of extra time, actually, because I budgeted 10 minutes. So let's also talk about diffusion. So let's say you're standing in a room, okay? That's you. And then someone else is standing on the other side of the room. Okay, and they had a lot of beans, so they fart. That's a fart. Okay, now let's zoom in to this fart. Okay, now these fart molecules, because they're gases, are under random molecular motion. And so because they're going randomly, eventually they're going to spread out. So they're going to spread out this way, and this way, and this way, and this way, and this way. And they lower in concentration as they spread out. But still, eventually, some of these fart particles are going to reach your nose, right? And then you're like, ew. And this process is called diffusion. So it's important that you remember it's driven by random molecular motion for gases, and they spread out evenly, and there you go, diffusion. So this happens with perfume, with food. Happens faster when you have faster particles. So high temperature will speed up diffusion. All right. Do the 2 practice problems, and then play the next video about atoms.